Preparing for a data engineering at New Relic interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a scalable pipeline for ingesting New Relic telemetry data? I would separate ingestion from processing using durable message buffers such as Kafka. Stateless collectors would validate envelopes, attach tenant metadata, and partition records by account and suitable entity keys. Stream processors would normalize, enrich, and route data into query-optimized storage. I would add quotas, backpressure, retries with dead letter topics, and idempotent writes. Metrics for lag, rejection rate, throughput, and end-to-end latency would expose failures early. The design must scale horizontally without allowing one customer to overwhelm shared infrastructure. While answering, cover event volume, schema design, partitioning, buffering, batch versus streaming ingestion, backpressure, durability, deduplication, validation, observability, and tenant isolation for logs, metrics, traces, and events. Question 2. What are the most important differences between batch and stream processing for observability data? Batch processing collects data and computes results periodically, making it efficient for historical reports, backfills, and large transformations. Streaming processes events continuously, which is essential for near real-time alerting and dashboards. Streaming introduces windowing, out-of-order records, state management, and operational complexity. Batch is simpler but increases freshness delay. I would use streaming for detection and customer-facing telemetry, then batch jobs for reconciliation, aggregates, retention management, and analytics requiring complete historical data. Make sure to cover latency, completeness, cost, windowing, late events, replayability, operational complexity, use cases such as alerting versus reporting, and how you would combine both models. Question 3. How would you handle late arriving and out-of-order telemetry events? I distinguish event time from processing time and assign each event a timestamp at the source. Stream processors use watermarks to estimate when a window is complete while accepting a configured lateness threshold. Events arriving within that threshold update state. Later events trigger correction or reconciliation paths. I would retain raw data for replay, use deterministic event identifiers for deduplication, and monitor lateness distributions. The threshold should balance dashboard freshness against aggregate accuracy for each telemetry type. In your answer, discuss event time versus processing time, watermarks, allowed lateness, window state, corrections, idempotency, replay strategies, and the product impact of inaccurate real-time aggregates. Question 4. Explain how you would design an idempotent data pipeline. Idempotency means processing the same input repeatedly produces the same final result. I would require a stable event ID, use deterministic transformations, and write results with an upsert or conditional insert strategy. A deduplication key could combine tenant, event ID, and schema version, with retention aligned to retry and replay windows. I would not promise exactly once delivery casually. Instead, I would build effectively once outcomes through durable offsets, idempotent syncs, and recovery testing. Be sure to mention stable event identifiers, deduplication stores, deterministic transformations, transactional boundaries, retries, exactly once versus effectively once semantics, and handling partial failures across pipeline stages. Question 5. How would you choose partition keys for a high-volume Kafka telemetry topic? The partition key should preserve only the ordering the application truly needs. For telemetry, I might use a composite of account and entity, then hash it to distribute traffic. Account-only partitioning simplifies ordering but creates hot partitions for large customers. Random partitioning improves balance but loses entity ordering. I would measure cardinality and skew, size partitions for peak throughput, and keep enough parallelism for consumers. Key changes require a migration plan because they alter ordering and replay behavior. Focus on distribution, ordering requirements, tenant skew, hot partitions, consumer parallelism, key cardinality, rebalancing, retention, and whether ordering is required per entity, account, or event stream. Question 6. How would you model telemetry data for efficient analytical queries? I would keep an immutable raw layer for replay and a curated layer optimized for query patterns. Each record should include tenant, timestamp, entity identifiers, metric or event attributes, and schema metadata. Time-based partitioning supports retention and pruning, while columnar storage and compression reduce scan cost. I would avoid indexing every arbitrary attribute, especially high cardinality values. Instead, I would identify common filters, maintain selective indexes or projections, and monitor query plans continuously. Cover raw versus curated layers, wide events, normalized dimensions, time partitioning, indexing, compression, cardinality, retention tiers, query patterns, and avoiding schemas that make common observability queries expensive. Question 7. What is high cardinality, and how would you control it in an observability platform? Cardinality is the number of distinct values in a dimension, such as user IDs or request URLs. High cardinality can multiply index size, memory usage, and query cost, even when event volume is moderate. I would normalize dynamic paths, apply limits and quotas, separate searchable attributes from payload fields, and aggregate metrics where appropriate. I would provide visibility into the most expensive dimensions rather than silently dropping data. Control should protect the platform while preserving diagnostically valuable context. In your answer, define cardinality, explain its effects on storage and query performance, distinguish useful dimensions from unbounded values, and propose quotas, aggregation, filtering, and customer feedback mechanisms. Question 8. How would you design a data quality framework for telemetry pipelines? I would define quality contracts for each source, required fields, valid types, timestamp bounds, acceptable null rates, uniqueness expectations, and freshness targets. Validation would happen at ingestion, with malformed records quarantined and counted rather than silently discarded. Downstream checks would detect volume changes, distribution shifts, duplicate rates, and missing partitions. Alerts need severity and ownership, not just thresholds. I would version contracts, provide producer feedback, and allow carefully documented degradation when rejecting data would worsen an incident. Mention schema validation, completeness, uniqueness, freshness, distribution checks, semantic rules, quarantine paths, quality dashboards, ownership, alert thresholds, and balancing strict rejection against graceful degradation. Question 9. How would you optimize a slow SQL query over billions of telemetry records? I would first inspect the execution plan and query profile rather than guessing. I would ensure time and tenant predicates enable partition pruning, select only required columns, and push filters before joins. If repeated aggregations dominate cost, I would add materialized rollups or pre-aggregated views. Large joins may require broadcast, repartitioning, or denormalization depending on sizes. I would test with production-shaped data, compare latency and resource usage, and protect shared workloads through quotas or workload isolation. Be sure to cover query plans, partition pruning, predicate pushdown, column selection, join strategy, pre-aggregation, materialized views, approximate functions, concurrency, and validating improvements with representative workloads. Question 10. What strategies would you use to manage schema evolution in a data platform? I prefer schemas that evolve additively. New optional fields, stable meanings, and explicit defaults. A schema registry can validate compatibility and publish versions, while producers and consumers run contract tests before deployment. For incompatible changes, I would introduce a new version, dual read or dual write during migration, and deprecate the old contract after usage falls to 0. Documentation must explain semantic changes, not merely field types. This prevents silent analytical corruption, which is often more dangerous than pipeline failure. Discuss backward and forward compatibility, versioned contracts, additive changes, field deprecation, registry governance, migration tooling, consumer testing, and handling incompatible changes without interrupting ingestion. Question 11. How would you ensure reliable exactly once or effectively once processing? Exactly once semantics require coordination across source offsets, processing state, and the destination, which can be expensive or impossible across independent systems. I usually target effectively once results, checkpoint after durable work, use transactional or idempotent syncs, and key writes by deterministic event IDs. On restart, replay is safe because duplicates collapse. I would document where duplicates or losses remain possible, test crashes between every boundary, and prioritize correct customer visible aggregates over a misleading delivery label. Explain delivery semantics, checkpointing, offset commits, transactional writes, idempotent syncs, failure windows, replay behavior, and why business-level correctness matters more than claiming exactly once guarantees. Question 12. How would you monitor and troubleshoot a data pipeline in production? I would instrument every stage with throughput, processing latency, queue lag, error counts, retry volume, freshness, and resource utilization. Correlation IDs and structured logs should connect an input event to downstream outcomes. Data quality metrics reveal silent failures that infrastructure dashboards miss. During an incident, I would identify whether the bottleneck is source traffic, broker capacity, processor state, storage, or query concurrency. Runbooks should include safe replay, throttling, isolation, and customer communication procedures. Cover throughput, lag, error rate, freshness, completeness, backpressure, resource saturation, trace correlation, structured logs, lineage, runbooks, and distinguishing source, processing, storage, and query failures. Question 13. How would you design retention and deletion for customer telemetry data? I would represent retention as tenant-aware policy metadata and enforce it at every storage layer. Time-partitioned data enables efficient expiration, while older data can move to cheaper storage if product requirements allow. Deletion requests must cover raw records, indexes, aggregates, caches, backups where applicable, and derived datasets. I would track deletion jobs with auditable status and retries. The design should minimize unnecessary copies, because every replica or materialized view becomes another place where retention can fail. Mention tenant-specific retention, hot and cold storage, legal deletion, partition expiration, tombstones, backups, derived data, auditability, cost controls, and proving deletion actually propagated across systems. Question 14. How would you prevent noisy or abusive tenants from affecting other customers? I would enforce limits at the edge using per-tenant rate quotas, payload size checks, and concurrency controls. Shared queues need fair scheduling so a high-volume account cannot consume all capacity. I would isolate especially expensive workloads through partitions, resource pools, or separate processing lanes. The platform should expose usage and rejection reasons, apply retry-friendly responses, and preserve critical traffic during overload. I would continuously test noisy neighbor scenarios because isolation is a measurable reliability property, not just an architectural intention. Focus on tenant isolation, ingestion quotas, rate limiting, fair scheduling, partition strategy, resource pools, admission control, monitoring, graceful degradation, and transparent customer-facing limits. Question 15. How would you build a backfill pipeline without disrupting real-time ingestion? I would treat backfills as replayable, lower-priority workloads with separate capacity or strict resource quotas. The job would process bounded time partitions, checkpoint progress, and write idempotently using the same transformation version as production. Throttling protects real-time consumers, while metrics track completion, lag, failures, and output reconciliation. Before launching broadly, I would test a small range and compare aggregates. If logic changes, I would version outputs explicitly rather than silently replacing current data. Discuss separate compute capacity, throttling, checkpointing, idempotency, time range partitioning, priority queues, validation, monitoring, and ensuring backfilled results do not overwrite newer or corrected data incorrectly. Question 16. What role does Apache Spark play in a modern data engineering platform? Spark is useful for distributed batch transformations, large joins, aggregations, and historical backfills because it parallelizes work across a cluster. I pay close attention to shuffles, skew, partition sizing, serialization, and repeated scans. Spark structured streaming can support continuous processing, but it is not automatically the best choice for low-latency telemetry paths. I would use a specialized stream processor when latency and stateful event handling dominate, and reserve Spark for scalable analytical computation. Cover distributed execution, batch transformations, joins, aggregations, shuffles, partition sizing, memory management, streaming limitations, and when simpler SQL engines or specialized stream processors are preferable. Question 17. How would you design a reliable data lakehouse architecture for observability analytics? I would organize the lakehouse into immutable bronze data, validated silver data, and business-ready gold datasets. Open columnar formats reduce lock-in, while transactional table layers provide atomic commits, schema enforcement, and reproducible reads. A catalog should track ownership, lineage, and retention. I would compact small files, partition by time and tenant appropriately, and separate interactive serving from heavy historical computation. The lakehouse is excellent for durable analytics, but latency-sensitive queries may need specialized serving storage. Mention immutable raw data, curated tables, open formats, ACID transactions, cataloging, partitioning, compaction, schema governance, time travel, cost management, and separating analytical workloads from serving paths. Question 18. How would you protect sensitive data in logs and telemetry? I would minimize sensitive fields at collection and classify data before it enters shared infrastructure. Known patterns such as tokens, emails, and payment data can be masked or tokenized, but rules need testing to limit false negatives and positives. Encryption protects data in transit and at rest. Authorization should enforce tenant and role boundaries. I would audit access, scan samples and schemas, and define deletion workflows. Prevention at ingestion is safer than trying to clean every downstream copy. Be sure to discuss data classification, minimization, masking, tokenization, encryption, access control, tenant boundaries, audit logs, secrets detection, retention, and preventing sensitive values from entering downstream systems. Question 19. How would you test a data pipeline before releasing a major change? I would test transformations with deterministic unit cases and golden datasets containing duplicates, nulls, late events, malformed records, and schema changes. Integration tests would exercise brokers, checkpoints, sinks, and failure recovery. I would replay production-shaped samples, compare distributions and aggregates, and benchmark throughput, latency, and cost. Shadow processing can reveal differences without affecting customers. Before release, I need a rollback or version switch, plus clear acceptance thresholds for correctness and operations. Cover unit and integration tests, contract tests, replay testing, property-based checks, golden datasets, performance benchmarks, failure injection, shadow traffic, rollback, and validating both data correctness and operational behavior. Question 20. Describe a trade-off you would make when building a real-time observability data product. For real-time alerting, I might accept approximate aggregates and a small late data correction window to keep latency predictable and infrastructure affordable. Exact historical results can be recomputed asynchronously from durable raw events. I would make that trade-off explicit through freshness and accuracy objectives, expose correction behavior to users, and monitor false alerts, lateness, and compute cost. If customer impact grows, I could increase precision selectively for critical signals rather than making every query expensive. In your answer, explain a concrete trade-off involving latency, accuracy, cost, durability, or feature breadth. Justify the decision with workload requirements, measurable objectives, and a mitigation plan. If you are still with us, congratulations, You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.